In the previous class, the overall efficiency of compressor and turbine was explained. The overall efficiency can be related to the small stage efficiency using appropriate relations. The compressor can have several stages, and for each stage we can define small stage efficiency. Or if a compressor does not have stages, we can hypothetically assume that the compression is carried out in small stages. So for the stage we define efficiency. This is the relation. The actual temperature rise in a turbine stage is delta Ts, and the ideal temperature rise in a stage is delta Ts dash. So if we divide the ideal temperature rise in a stage with stage efficiency, we will get the actual temperature rise in a stage, and after the summation we will get the total actual temperature rise. The stage efficiency is assumed to be same for all these stages, so we can remove this eta s out of the summation sign and we will get summation delta Ts dash. From the previous topic we obtained this relation: actual temperature rise total is equal to total ideal temperature rise divided by the compressor isentropic efficiency. After solving these two, we will get a relation between stage efficiency of a compressor and the overall efficiency of the compressor. You can see the different temperature differences in this figure. In this figure we can see delta T dash. So delta T dash is the ideal overall temperature difference. Then we have delta Ts dash. Delta Ts dash is the ideal temperature rise in a stage. But when we are calculating or when we are determining delta Ts dash, our initial point is the actual point of the previous stage. This is the actual point of the exit of the stage, and we are obtaining delta Ts dash using this actual point. So this is a vertical line. The difference in height of this vertical line is delta Ts dash. Now we have delta Ts. Delta Ts is the actual temperature rise in a stage, and delta T is the actual overall temperature rise. So when we sum delta Ts for every stage, there are 4 stages in this compressor, the summation will give the value delta T. But here in delta Ts dash, if we take the sum of 4 stages, delta Ts dash for all the 4 stages, then it will not be equal to delta T dash, because this vertical line and this vertical line, if we consider this vertical line at this entropy and if we consider this vertical line, both will have difference in heights. So delta Ts dash for a stage is not simply as delta T dash for a stage on this line. So based on this reason, due to this reason, the stage efficiency of a compressor has a greater value when compared to the overall efficiency of the compressor. For the turbine, the case is opposite. The overall efficiency of the turbine is greater than the stage efficiency. For the case of compressor, the turbine, for the case of compressor, the temperature is increase. When temperature is increase, there is additional heating and it requires more compressor work. In the case of turbine, when the temperature is increased, it results in more work. So for that reason, the overall efficiency of turbine is greater than compared to stage efficiency of the turbine. The duration of the stage or the region of the stage can be further reduced, and we can assume very small stages. We can hypothetically divide the entire compression step into very small stages. For the very small stage, we have polytropic efficiency. So differential temperature rise ideal divided by differential temperature rise actual, and this will be constant for all these stages. This is the isentropic relation. If the process is ideal, this is the isentropic relation, and we can differentiate this relation for the isentropic conditions. So here we have dt dash, this is the ideal small temperature rise. Then we solve 1 and 2. After solving 1 and 2, this is our equation. Then we integrate, and after integration, this is our equation through which we can determine the polytropic efficiency of a compressor stage. Then we can write this equation in log form into exponential form. This is the basic definition of compressor efficiency. In this definition, this is the ideal temperature ratio. The ideal temperature ratio can be written using the isentropic relation. This is the actual temperature ratio. For the actual temperature ratio, we are writing the pressure ratio in terms of polytropic efficiency using this formula. For simplicity, the exponent used along with the actual static pressure, we can, for simplicity, we can write n minus 1 over n. So instead of using gamma eta infinity c, we can write n, and similarly instead of using gamma, we can write n. So this relation is for the compressor. Similar relation can be written for the turbine. So this is the ideal term, and this is the actual term which is written in terms of polytropic efficiency. Now for the purpose of example, suppose the polytropic efficiency is 85%. The variation in the isentropic efficiency is shown in the figure. The compressor efficiency, isentropic efficiency, or turbine isentropic efficiency depends on the number of stages. So as the number of stages increase, the pressure ratio increases, the compressor efficiency, overall efficiency is decreased. But here the polytropic efficiency is 85% for all the stages. Similarly, polytropic efficiency is 85% for turbine, but the overall efficiency increases with the increase in pressure ratio. So this is one of the factor which is in the real cycles. In the real cycle, the efficiency is not 100%, and we have to modify our relations to calculate the actual performance of the gas turbine cycle. Another difference between actual and ideal cycle is that the specific heat and ratio of specific heat is not constant. The specific heat increases with the increase in temperature. So specific heat of the fluid in the turbine will be more when compared to the fluid which is in the compressor. Similarly, the fuel-air ratio also changes the specific heat. Increase of fuel, addition of fuel will result in increase of specific temperature, specific heat. The ratio of specific heat reduces with the increase in temperature, and the specific heat ratio increases with the increase in air fuel ratio. So this is another difference when we study real cycles in comparison to the ideal cycles. The cycles which are previously discussed are for the general case, usually considered for the stationary power cycles. The gas turbine cycles for propulsion applications slightly differ. The reason is that the useful power is in the form of thrust rather than the shaft power. The thrust is generated using the propelling nozzles in case of turbojet and turbofan engine. In the case of turboprop, the thrust is generated using a propeller. So turbine is driving the compressor as well as propeller, and that propeller is resulting in thrust. The contribution of the exhaust nozzle is relatively less. So this is one difference. The objective in case of propulsion applications is to have thrust rather than the electricity. Second feature due to which there is difference between shaft power cycle and propulsion cycle is that we have to consider the forward speed of the airplane, and secondly the altitude is also important. So there is speed of engine, there is altitude on which it is flying. There are differing requirements for takeoff, climb, cruise and maneuvering. For the analysis of the airplane cycles, suppose this is the computational, control volume, and this is the power unit. There is ambient pressure in the surrounding region. The air is coming in with a velocity of Ca, and the fluid is discharged with a high velocity of Cj. So the value of Cj, the jet velocity, is greater than the inlet velocity Ca. Similarly, the pressure can differ. At the inlet, the pressure can be Pa, and the outlet pressure can be Pj, that is the jet pressure, and sometimes the nozzle expands the fluid such that the pressure at the exit is same as the ambient pressure. But the difference of Cj and Ca is always there. Now we make an assumption that the mass flow rate is constant. We neglect the addition of the fuel mass, and we write a relation for the thrust. So thrust is equal to mass flow rate multiplied by the difference in velocity. This thrust relation is due to momentum. This is momentum thrust. If there is difference in pressure, that is Pj is greater than Pa, then there is additional thrust due to pressure. So modified relation consists of momentum thrust and pressure thrust. Pressure thrust only occurs when the fluid is not expanded to pressure Pa. If the fluid is not fully expanded, then it will result in pressure thrust. Now we assume that the pressure thrust is negligible when compared to the momentum thrust. In this case, we can have several useful relations. The efficiency of the aircraft cycle is determined using a parameter which is called propulsion efficiency. The propulsion efficiency is the ratio of useful propulsive energy or thrust power to the available kinetic energy. So there is available kinetic energy due to the working of the engine. The available kinetic energy is in the denominator. So this is available kinetic energy. All the kinetic energy available is not converted into thrust. This is the formula for calculation of the thrust power. The force thrust multiplied by Ca gives the thrust power. So the division will give the propulsion efficiency. The denominator can be written in terms of two components. This one is the useful component and this one is the unused component of kinetic energy. By solving these two, we get this formula. So propulsion efficiency is not the overall efficiency. In next few slides, there are other efficiency discuss which will show the overall efficiency of the aircraft power plant cycle. Using this relation, we can have important information. If Ca is equal to 0, if Ca is 0, then propulsion efficiency becomes 0. But when Ca is 0, the thrust is maximum. In this formula, if Ca is 0, the thrust is maximum. But in that case, the propulsion efficiency is 0. The reason is that when the value of Ca is 0, this means the airplane is not moving. When it is not moving, then it can have thrust. But the thrust power is product of thrust multiplied by velocity of the airplane. So when airplane is not moving, then thrust power will be 0. Even though the thrust is maximum, but the thrust power will be equal to 0. Second possibility is that Ca is same as Cj. The two velocities are same. When the two velocities are same, the efficiency is maximum, but the thrust is 0. When Ca and Cj are same, then inlet velocity and outlet velocity of the fluid both are same. In that case, the thrust is 0. So the value of Ca should not be 0 and it should not be equal to Cj. It should be intermediate, so that we have suitable value of propulsion efficiency along with the suitable value of thrust power. There are various types of engines that can be used for aircraft applications: piston engine, turboprop, turbofan, turbojet, ramjet. Among these, the piston engine can have maximum mass flow rate using this type of propeller, but the value of velocity is very less in case of piston engine. So piston engine is not common due to the weight and less power. Higher weights but less power, the piston engine is not utilized. Ramjet engine is not independent, so for that reason it is not put into the comparison. The independent aircraft engines are turboprop, turbojet and turbofan. We can see the ranges of altitude and Mach number in which they are efficiently used. Suppose turbojet engine is used when the altitude is between 15,000 to 20,000 and Mach number is in the supersonic range. Turbofan engine is for the altitude about 10,000 and Mach number is in the high subsonic range. Turboprop engine is in the middle subsonic range and the altitude is 5,000. If these engines are operated outside this regime, the efficiency of these engines will be less. The thrust and fuel consumption of a jet propulsion engine vary with both cruise speeds and altitude. So the suitable altitudes and Mach number are given in this chart. Other than propulsion efficiency, there is another efficiency which is termed as efficiency of energy conversion. So it is the kinetic energy or rate of kinetic energy divided by heat supplied. Heat supplied is due to the fuel. So this is fuel energy or thermal energy generated from the fuel, and this one is the kinetic energy. So this kinetic energy is total whether it is utilized or not. The efficiency of energy conversion is kinetic energy divided by the fuel energy. Then overall efficiency is the thrust power divided by the rate of heat supplied due to the fuel. So overall efficiency is equal to energy of conversion, efficiency of energy conversion multiplied by propulsion efficiency. The various engines are compared based on two different conditions. One is the sea level static performance, which is for the aircraft take-off requirements, and second comparison is based on the cruising conditions at optimum speed and altitude. So we can compare two or more than two engines based on these two conditions. Another parameter which is more useful is specific fuel consumption. So specific fuel consumption is fuel consumption per unit thrust. We can relate the overall efficiency and specific fuel consumption using this formula. So overall efficiency and specific fuel consumption we can see over here. So specific fuel consumption is obtained by mass of fuel and divided by thrust. So mf divided by m Cj minus Ca, m multiplied by Cj minus Ca divided by mf. So this will be replaced with specific fuel consumption. So overall efficiency depends on ratio Ca over CFC, because this is related to the fuel. For a particular fuel this will be constant. Another parameter, specific thrust, is thrust divided by unit mass of flow of air, and specific thrust is utilized for comparing different engines. We can compare the thrust divided by mass flow rate of air, because mass flow rate of air and the size of the engine is directly related. So if the specific thrust of a particular engine is more, then it will be more desirable. The size and the mass flow rate of air is related to size, and size is related to the weight of the airplane and also the drag, because if the size is more, the magnitude of the drag is also higher. We can relate the specific fuel consumption with specific thrust using this formula. The small f is fuel air ratio mf/m, and specific thrust is Cj minus Ca. As previously mentioned that the performance will be different at different altitudes, so we have to perform calculations about various parameters such as Mach number at different altitudes. For example, if the plane is moving, the aircraft is moving with a certain value of velocity. So for a particular value of velocity, the Mach number can be different at sea level and at higher altitudes. Suppose the value of velocity is 600 meter per second. The Mach number at sea level will be around 1.6, but at this higher elevation it will be around 2. The reason is that at higher altitudes the temperature decreases. When temperature decreases, the sonic velocity is decreased. When sonic velocity is decreased and the inlet velocity or velocity of airplane is same, then Mach number will increase. The design of the intake and propelling nozzle is also important in the airplane cycles. The purpose of the intake section is to provide air at a suitable value of velocity and pressure, and this is required to have the optimum performance of the compressor. So intake and nozzle are considered as a separate components. So here we can see the gas turbine cycle with separate locations for A and 5. The speed of the airplane can be different. At takeoff, the inlet velocity is less, and while cruising, the inlet velocity to the engine is higher. So intake section is critical for the gas turbine designs for the airplane applications. The purpose of the intake is to minimize the pressure loss and to have the uniform flow pattern and uniform pressure so that the compressor can work efficiently. And the uniform pressure and velocity is required at all the flight conditions. If the velocity or the flow is non-uniform, distorted, then it can create the major pressure variations with respect to time in the compressor section. So this will cause compressor surge, and finally it can result in major mechanical damage, because the variation in pressure, major variation in pressure can result in vibration and it can damage the different components of the engine. Usually we require the Mach number between 0.4 to 0.5. So this is the optimal Mach number or optimal velocity can be calculated for the compressor section. Then there can be different flow patterns at the inlet of the inlet section. This is one flow pattern which is during static conditions. In the static conditions, the ambient velocity is negligible, and we have to bring the fluid or air with a sufficient velocity inside the compressor section. So this is insufficient air, due to which the flow is sucked and the flow is sucking. So this is the converging form of flow pattern. When the airplane is moving, the fluid will enter with a sufficient speed and it will not require any major change in the flow velocity before reaching the compressor. This is another flow pattern when the airplane is moving with high velocity and this high velocity is undesirable for the compressor, so we have to reduce the speed, and the reduction in speed will be created, and this will resulting in a diverging flow pattern. So this involves acceleration of the flow, and this involves deceleration of the flow.